In this video, we are going to solve a simple thermodynamics problem that contains a piston cylinder. Let's begin. A mass of 5 kilograms of saturated liquid vapor mixture of water is contained in a piston cylinder arrangement at 125 kilopascals. Initially, 2 kilograms of the water is in the liquid phase and the rest in the vapor phase. Heat is now transferred to the water, and the piston, which is resting on a set of stops, starts moving when the pressure inside reaches 300 kilopascals. Heat transfer continues until the total volume increases by 20%. And then we have to draw a PV diagram. We need to find the initial and final temperature, find the mass of the liquid water once the piston starts moving, and the work that is done during the process. Let's go ahead and draw what is going on because that's going to help us, and the different states that we have. So initially, we have a piston cylinder, and the piston is resting on a set of stops. Initially, it's at 125 kilopascals. P1 equals 125 kilopascals. What else do we know? We know that it's a saturated liquid vapor mixture at the beginning. So the phase is saturated mixture. And we already know that when we have saturated mixture, we're probably going to have to find the quality at some point. We know that the mass is 5 kilograms. What else? Oh, we know that 2 kilograms of the water is in the liquid phase and the rest in the vapor phase. So mass of the liquid is 2 kilograms. And then the rest is vapor. So 5 minus 2, 3. So 3 kilograms are in the vapor phase. Alrighty, so that's the first thing that's happening, right? Let's go ahead and figure out what the next phase is. And this is where everyone or a lot of people mess up at the beginning. They see it as a problem with 2 states when it actually is a problem with 3 states. So in the second state, it's when the piston's about to start moving. It's not quite moving yet, but it's about to, like right before it starts moving. So in this state, the pressure is 300 kilopascals because that's when it starts moving. Starts moving when the pressure inside is 300 kilopascals. So P2 is 300 kilopascals. Mass, it's a closed system, right? So the mass is still 500 kilograms. Nothing is coming in or out of the piston cylinder. So far, I think that's all we know. And then the third phase, oops, just kidding. In the third phase, it actually starts moving, right? It's all the way up here. It's off the stops. The pressure is still 300 kilopascals. And it stopped moving when, and still closed system, right? So 5 kilograms. And it stopped moving when the volume increases by 20%. So we'll represent volume of 3 by the volume of 1 times 1.2. Alrighty. So in order to draw our PV diagram, we need to know what phase these 3 states are in, right? So let's go ahead. Also, let's see here. So we know it's a closed system, right? Closed system. Closed, right? So that means M1 equals M2 equals M3. And we also know that the volume in 1 and then the volume of 2 are the same, right? Because it's still resting on these pistons. So we know that V1 is equal to V2, right? Since piston does not move. So we know that V1, or the specific volume, is equal to V2, right? Because specific volume is equal to volume over mass, right? So if we can figure out the specific volume in phase 1, we can figure out the specific volume in phase 2, which is good because in order to look up the states in our tables, we kind of need to know either pressure and temperature, specific volume, or later on internal energy or enthalpy and stuff like that. And right now we don't have those. So let's go ahead and mess around with our first state so that we can figure out the specific volume. So in order to figure out the specific volume, we'll need quality. And fortunately for us, we know that the quality formula is also the mass of the substance that is in the vapor phase divided by the total mass of the substance. So the mass in the vapor phase is 300 kilograms, and the total mass in phase 1 is 5 kilograms. So we get a quality of 0.6. And then to find our specific volume for state 1, we'll need the formula of quality times the specific volume of the saturated vapor plus 1 minus the quality of the specific volume of the saturated liquid. And we get those values in table 5.2, properties of saturated water, pressure table. Alright, so we pull that up, and we see here, in order to look these values up, we're going to look up the pressure at 125 kilopascals since it's a saturated mixture. So 125 kilopascals is right here. Great. And we need the saturated liquid specific volume and the saturated vapor specific volume. Alrighty. So our V. So we have our saturated, we have our saturated liquid specific volume, which is 0.001048 meters cubed per kilogram. Our specific volume of the saturated vapor is 1.37490 meters cubed per kilogram. We'll go ahead and plug those into our formula that we have there. And we get specific volume is equal to 0.6 times 1.3749 plus 1 minus 0.6 times 0.001048. Alrighty. And after plugging that into your calculator, you get 0.8254. So specific volume of state 1 is 0.8254 meters cubed per kilogram. Perfect. So with V, if we know that specific volume in state 1 is that, we also know what the specific volume at state 2 is. So 0.8254. Great. Perfect. So let's go ahead and move this down a little bit. So we know that V1 and V2 are the same, right? Because, again, the piston cylinder does not move. It's still on the set of stops. So we know that V1 is equal to 0.8254 meters cubed per kilogram. And we also know that V2 is equal to 0.8254 meters cubed per kilogram. Perfect. And now, since we have specific volume and the pressure in state 2, we can figure out the state. So let's go ahead and do that. So we'll figure out state 2. We have that the our pressure in state 2 is 300 kilopascals, and the specific volume is 0.8254 meters cubed per kilogram. So we're going to go ahead and look up the pressure at 300 kilopascals in table 5.2, the same as the last one, and we're going to go ahead and compare the specific volumes of the saturated liquid and the saturated vapor to the specific volume that we have for V2. Alrighty, so just a reminder, I cut off the title, so this is pressure, temperature, specific volume of the saturated liquid, specific volume of liquid vapor, and specific volume of saturated vapor. Alrighty, pressure at 300 kilopascals is right here, so we'll be looking at these two. We see that our specific volume is larger than the specific volume of the saturated vapor. So that means that our state 2 is a superheated vapor. Superheated vapor. And if you don't remember why or how to do that, make sure you watch some of my past videos. I post a little cheat sheet about how to figure that out quickly. Alrighty, state 2, superheated. Great. Now let's go ahead and find the state 3. Find state 3. In state 3, we have that the pressure is equal to 300 kilopascals. We also know that the mass, it's a closed system, right? So mass is still 5 kilograms. And we know that the volume in state 3 is equal to the volume of state 1 times 1.2. We can find the volume of 1 because we have that the specific volume at state 1 is 0.8254 meters cubed per kilogram. And we know that the mass in state 1 is 5 kilograms, right? Since specific volume is equal to the volume divided by mass. So volume is equal to specific volume times mass. We plug in what we have, so the specific volume of 0.8254 times the mass of 5 is equal to 4.127 meters cubed. Alrighty, so that's the volume in state 1, and we're going to go ahead and multiply that times 1.2 since it increased by 20%. It was told to us in the problem statement. So times 1.2 is going to give us that it's going to give us 4.9524. So volume in state 3 is 4.9524 meters cubed. And in order to figure out the state and look it up in our saturated tables, we need two values, either pressure, temperature, specific volume, enthalpy, internal energy. Here we don't have specific volume, we have volume, but we can figure out the specific volume using our mass in state 3 and our volume at state 3. So again, specific volume is equal to volume over mass. And we go ahead and plug those in like this. And we get our specific volume at state 3, which is 0.99048 meters cubed per kilogram. And now that we have that, we can look it up in our tables, right? We are going to look up the pressure at 300 kilopascals and compare V, or specific volume 3, with specific volume of the liquid and specific volume at the vapor or saturated vapor. Okay, so we're gonna look that up in table 5.2. Table 5.2. So over here, the same one. So I see here that my specific, it's still the same numbers, right? Because it's still at 300 kilopascals. So my specific volume for saturated liquid is 0.001073. And for the vapor, it's 0.60582. Again, these are from the graph, from the table we just looked at. In hours, where the specific volume at state 3 is 0.99048. We see that our specific volume is greater than the specific volume at the saturated vapor, so that means that state 3 is superheated. So I'm going to go ahead here and label it superheated. And also, I'll put the value for specific volume at 0.99048. Alrighty, perfect. So now that we have our phases, we're going to go ahead and start answering question 1, which is draw a PV diagram, a pressure specific volume diagram. So here we are. We're going to go ahead and look for our first point. In our first state, it's a saturated mixture. Quality is 0.6, so it's going to be a little bit towards the right. So I'm going to go ahead and I'm just going to put it right here. I'll put it right there as my first state, where the pressure is 125 and my specific volume is 0.8254, right? Yes, great. Now I'm going to go ahead and work on my state 2. And this is at some temperature, right? I don't know what the temperature is just yet, and I'm probably going to have to figure that out very soon. At a temperature of who knows what. And then my state 2, we see that the pressure changed, but that the specific volume remained the same, right? So since the specific volume is still the same, it's going to be right on top of the 1, right? Because it's still the same specific volume. However, pressure did change. It's now going to be at 300 kilopascals. So I'm going to go ahead. That's going to be my state 2. And that is going to be at some temperature, right? I don't know what that temperature is. And then my state 3 is still superheated, right? So it's going to be on the right side of my dome, right? Just like state 2. But this one's at the same pressure, different specific volume. And it's a greater specific volume. So it's going to be to the right of it. And so it should be right here. Remember, because the pressure is still at 300 kilopascals. It's just that the specific volume is now at 0.99048. So that's going to be my third state. I'm going to go ahead and just connect them and draw little arrows to show where it started and where it goes, right? Okay. So that was for A. That was the answer for A. Now let's go ahead and start answering B. B asks, what is the initial and final temperature? Okay, so in my initial state, we have it being a saturated mixture. So that's really easy to look up, because if it's a saturated mixture at 125 kilopascals, it means that the temperature for the saturated mixture has to be 105.99, because water only exists as a saturated mixture at 125 kilopascals at a temperature of 105.99 degrees Celsius. So that one was not that bad. So temperature at state 1 is 105.99 degrees Celsius. Perfect. That's one of our answers. Now we have to figure out the final temperature. And for the final temperature, we see here that we have it's a superheated vapor, right? So we're not going to be looking at our saturated water tables. We're going to look at our superheated water or superheated steam tables. So we're going to look up P3, or pressure at state 3 of 300 kilopascals, and where the specific volume is equal to 0.99048 meters cubed per kilogram. And that's going to be, in my textbook, it's table 5.3. Properties of superheated vapor. Okay, and this is how that table looks like. We're looking it up at 300 kilopascals, which is right here. Perfect. And where the specific volume is 0.99048. So I'm going to go ahead and look at this column right here. I'm going to look for 0.99048, which I'm most likely not going to find exactly. And of course, obviously I cannot. But I can linear interpolate, right? Because I'm looking for the temperature. So my 0.99048 lands in between this guy and this guy. And their respective temperatures is 300 and 400. So I'm going to go ahead and interpolate to get what the temperature is at a specific volume of 0.99048. Alright, so I'm going to take a note of those values because they are needed in order to do the linear interpolation. So do linear interpolation. Perfect. Linear interp. Yes, that's fine. I'm going to set it up how I usually set it up, just how in like all my other videos. I'm going to put my specific volume here, all of my values, 0.87529. I'm looking for the specific volume at 0.99048. Or I'm looking for the temperature at the specific volume of 0.99048. And then my other bound is at 1.03151. Temperatures are at 300 and 400. I'm looking for what it is in between those two. And again, I'm going to use this formula right here. And just as a reminder, it's set up this way: x1, y1, x2, y2, x3, y3. I'm looking for y2. Reminder, so my x1 would be 0.87529. my Y3 would be 400. Okay, it's not that hard to tell which one is which. And then I would plug it into my equation or to my formula, and I'll get that Y2 is equal to 373.736. Just plug it into your calculator, figure out what it is. I recommend to either code it into your calculator or have an Excel or an online calculator do it for you so you don't have to waste so much time during an exam. So we get that our temperature at state 3 is 373.736 degrees Celsius. Alrighty, so that's question number 2, or question B. Let's see. Question C says, what is the mass of the liquid water when the piston first starts moving? Alrighty, so the piston first starts moving at state 2, right? That's when it's about to begin, right? And at state 2, it's superheated. And when a substance is superheated, it means that there is no liquid. There's no liquid in sight. In a saturated mixture or in a compressed liquid, yes, you do have liquid. But when it's superheated, everything is in the vapor state. So for C, right here, for question C, state 2 is superheated, which means that the mass, or the liquid mass, is equal to 0. So that was pretty easy too. Let's go ahead and look at the last question, question D. It says, what is the work done during the process? So just a friendly reminder, work happens when the piston is moving, right? So if the piston does not move, that means that no work has been done. So let's go ahead and go here. So reminder, work happens when piston moves, right? So from state 1 to state 2, the piston does not move, right? It's still on the set of stops, so no work. But from state 2 to state 3, that's when we have work, because that's when the piston moves. So the formula for work in a piston-cylinder arrangement is the following. So work is P times dV, so pressure times the change of volume. Again, another way of writing it is like this. From state 2 to state 3, right? Because from state 1 to state 2, there's no work happening. So the pressure times the volume at state 3 minus the volume in state 2. Alright, not too bad. I'm going to go ahead and plug in those numbers. So the pressure in from going to state 2 to state 3 is 300 kilopascals. So 300 kilopascals. 300 kilopascals. The volume at state 3 is 4.9524 meters cubed. Again, this is the volume, not the specific volume. So 4.9524 meters cubed minus our volume at state 2, or state 1, right? Because the volume in state 1 and the volume in state 2 are the same. So volume at state 1 is 4.127 meters cubed. We solve and we get 247.62 kilopascals times meter cubed. And then in case you don't remember, you didn't know, the conversion is at 1 kilojoules, which is the unit for work, is equal to 1 kilopascals times meters cubed. So our work is equal to 247.62 kilojoules. And that is the answer for question D. Alrighty, so that is it for today's video. I would say this is one of the easier piston cylinder problems, but it's good to know your basics. So hopefully you learned something, and good luck with your studies.